Much like life on Earth, stars have a beginning and an end. They don't shine forever. Instead, they follow a dramatic and captivating cycle over billions of years, evolving from their formation to an eventual spectacular finale. In the vastness of space, immense clouds of gas and dust drift. And if one of these clouds grows large enough, its own gravity pulls it inward, collapsing it in on itself. Near the center, the cloud becomes increasingly dense and hot. Eventually, the particles are pushed so close together that they begin to stick, to fuse. This fusion is the power source of a star. At that moment, the star switches on and begins to shine bright. Within every newborn star, hydrogen atoms fuse together to form helium, a process called nuclear fusion. This fusion powers each star, generating immense energy by combining these lighter atoms into heavier ones. Unlike fission, the reverse process, where we split atoms to produce nuclear energy, stars create their energy by merging atoms together. What happens to a star during the rest of its life depends on the size of the star at its birth. A star like the Sun exists in a delicate balance between two opposing forces: the inward pull of gravity, which tries to make the star collapse, and the outward pressure generated by energy from fusion reactions in its core. This equilibrium maintains the star's stability. When these forces fall out of balance, the star's behavior and life cycle begin to change. Eventually, the star's hydrogen supply runs out. Remember, hydrogen atoms are the fuel for the fusion reactions at the core of the star. Without hydrogen, fusion ceases, and energy production stops. At this stage, the star begins to collapse under its own weight as the outward pressure from fusion diminishes, allowing gravity to dominate and compress the star inward. The core becomes denser and heats up until it reaches a temperature high enough for helium to fuse. Helium fusion requires this extra heat due to its different atomic structure. It has a higher mass, and it leads to the formation of heavier elements, in this case carbon and oxygen. As the star begins to fuse helium, it releases additional energy, causing its outer layers to expand outward. The outer layers move farther from the core. The star's gravitational hold weakens, and it starts to shed these layers into space. The core's energy now surpasses the force of gravity, disrupting the star's balance and allowing it to expand further into what is called a planetary nebula, some of the most stunning structures in the universe. With its outer layers gone and its helium fuel exhausted for nuclear fusion, all that remains is the dense core, now known as a white dwarf star. One day our Sun will also expand dramatically, growing large enough to engulf the inner planets of the solar system, reaching even as far as Earth. At this stage, it will become a red giant, signaling the beginning of the end for our Sun. A white dwarf star is the dense, lifeless core left behind after a star like our Sun reaches the end of its life. This remnant holds about half the Sun's mass, but is compressed into a size similar to Earth, making it incredibly dense. With no nuclear fusion occurring, the white dwarf is technically dead, though it remains intensely hot. Over millions of years, it will slowly cool and eventually fade into a cold, dark, black dwarf star. Stars significantly larger than the Sun live vastly different lives. Their intense heat enables them to fuse increasingly heavier elements in their core, not just hydrogen and helium as smaller stars do. This fusion process causes the star to expand, with some growing up to 1,000 times the size of the Sun. Eventually, they fuse elements up to iron, the most compact and stable element. At this point, fusion can no longer provide energy, as breaking apart iron nuclei requires more energy than it releases. This leads to a core collapse, pulling the surrounding star inward until it rebounds, bouncing off the core, creating a massive shockwave. In an instant, a powerful supernova explosion occurs, propelling the outer layers of the star into space and scattering elements into the universe. For these super-large stars, all that is left after the supernova is a super-dense core known as a neutron star, an object that can have a mass greater than our Sun, but has a diameter of less than 20 kilometers. For these massive stars, we believe that when these dense cores finally collapse, the gravity is so strong it becomes a black hole. In summary, we've covered the life cycles of both large stars and smaller to medium-sized stars, like our Sun. Stable stars balance gravity's inward pull with the outward pressure from core fusion. When this balance shifts, due to changes in fusion energy, the star enters its final stages, evolving over millions of years. Stars are the factories of the universe, creating elements through fusion and supernova explosions. Amazingly, almost everything around you was formed inside a star billions of years ago, long before the Sun and planets existed. To conclude, let's review this diagram summarizing the life cycles of both large and small to medium stars. The key difference is that larger stars with their higher energy output end in a spectacular supernova and collapse into a black hole, while smaller stars gradually fade into black dwarf stars.